All right, welcome back, team. So this next thing is actually an 11.6, but I don't understand why. So we're going to do it now in 11.5, okay? So um, we're going to look at equation, let me zoom in, of the tangent plane for an equation of the form f of x, y, z equals some constant, okay? So let's recall that the equation of the tangent plane for z equals f of xy, okay, if you had a function like that, you remember the equation of the tangent plane, I think it was an 11.4, 11.3, it's in one of those. We've already done it though. That was z equals fx x0 y0 times x minus x0 plus fy x0 y0 y minus y0 plus z0. Okay, you remember that. Let's rewrite this. Okay, we're going to rewrite this as fx x. Oh, I've got copy and paste. Why not just do that? Okay, all that's the same, but we're going to have this is going to be minus z minus z0 equals 0. Okay, so what did we do? We took this z, subtracted it over here. This plus z, that's this minus, and that minus gives you plus z0. Okay? I want you to keep that in mind. Okay? Now, let's pretend we have an equation of that form. This is an implicitly defined relationship, not an explicit relationship. Okay? Now, we actually are assuming that z equals z of xy, but we don't know z. We don't know the function, right? So we already did this over here, right? We have these things, partial z with respect to x and partial z with respect to y. Math is more fun with sound effects, so you've got to make them. Okay? You don't really, but it's more fun for me, and I have to entertain myself sometimes. Okay. So what we're going to do is we're going to fit this into this. Or actually, we're going to fit this into this. So remember, here, z equals f of xy, right? So here, when we say partial of z with respect to x, that's going to take the place of this fx0, fx, x0, y0. So let's write it down. So we're going to copy and paste it. Let's get rid of the highlight. Okay. Now, what are we going to have here? Instead of f sub x, we're going to have partial of z with respect to x times x minus x0. Okay, this is of course taken at some x0, y0. Okay, write that better. Plus, this is partial of z with respect to y taken at some x0, y0. Minus z minus z0 equals 0. So far, so good, right? Okay, but let's replace this by this and this by this. What do we get? Let me put that in here just in case some of you are not listening to me talk and just looking at the notes to try to make it work. Okay, so putting that in there. Okay, so let me help you all there earlier. Okay, so now if you do that, you're going to get negative partial f with respect to x divided by, let's move that negative down, sorry, partial f with respect to z times x minus x0 minus partial f with respect to y divided by partial f with respect to z, y minus y0 minus z minus z0 equals 0. Okay, I'm going to go ahead and put pluses in there because, you know, why not? They've all got minuses. And now I'm going to multiply by the partial of f with respect to z. Okay, so what do I get? I get partial of f with respect to x times x minus x0 plus partial of f with respect to y times y minus y0 plus partial of f with respect to z times z minus z0 equals 0. That's got a nice little symmetry to it, doesn't it? Okay, so let's go ahead and do a problem. Oh, yes, let's do a problem. Let me highlight that because that's a big, important formula. Okay, so we're going to do number 36. This isn't again in 11.6. Okay, and we're going to have x to the fourth plus y to the fourth plus z to the fourth equals 3x squared y squared z squared. And we're going to find the equation of the tangent line equation of the tangent plane at 1, 1, 1. Okay? So, all we have to do, we're going to write this out as f of x, y, z equals x to the fourth plus y to the fourth plus z to the fourth minus 3x squared, y squared, z squared equals 0. Okay, so the equation is f of x, y, z equals 0 in this case. Okay, so when we have two things equal, that's what we're going to do. We're just going to put all the variables on one side, and you can put the constants on the other. But this is an implicit equation. Okay? Okay, so we're going to take our partial derivatives. Now, one thing I want you guys to notice, especially when we're doing things in multiple dimensions, is try to look and see if there's a symmetry. These x, y, and z, they all come in the same way, right? So if I take the derivative with respect to x, it's going to be the same thing when I do the derivative with respect to y and with respect to z. So partial f with respect to x is 4x cubed minus 6x y squared z squared. Okay, and I don't have to do the other ones because it's going to give me the same number. Especially even look, we're looking at it at 1, 1, 1. Okay, So now, let's take it at 1, 1, 1. That's going to be 4 minus 6, negative 2. Okay. This is also going to be negative 2. Okay. So what's our plane? The equation of the plane is going to be negative 2, x minus 1, minus 2, y minus 1, minus 2, z minus 1, wish I could write, equals 0. Okay. So what's that going to be? That's going to be, let me write that, that's negative, let me divide by 2. So I'm going to get, and divide by negative 2, x plus y plus z equals, I think it's 3. That 1's going to move over. Yep. Okay. This is also fine. It's not wrong. It's just this is better. Okay. But if you put this, on an exam, that wouldn't be wrong in normal times. But, if I'm giving you a multiple choice, I wouldn't put them both up there unless I made a mistake. Okay. Next question, we could actually also find the equation of the normal line at 1, 1, 1. That was actually the next part of this problem. Okay, I mean, that just becomes a line through 1, 1, 1 with direction also given by 1, 1, 1. Okay, so that just becomes what? X equals 1 plus t, y equals 1 plus t, z equals 1 plus t, which, surprise, surprise, we also have symmetric equations. X equals y equals z. Okay? All right. I'll see you all in the next set of videos.